Hello guys, welcome to homework number 5. I'll be going through the problems right now. The first one is focused on concept question 01, and it says two cars are traveling at the same constant speed v. Car A is moving along the straight section, so they're having constant speed, so they are not accelerating basically until we see what happens. And car B is rounding a circular turn. So once you are going in a circular turn, you can have a constant angular velocity. But you are still going to have a centripetal acceleration towards the center of the circle. So car B definitely has an acceleration. So car A is not accelerating, but car B is accelerating. That is correct. Car A is accelerating, but car B is not accelerating now. Both cars are accelerating now. The acceleration of both cars is 0 since they are traveling at constant speed. No. So the correct answer is A for that problem. Okay. Car A is not accelerating, but car B is accelerating. Next problem says the car, that's focused on concept question 02. The car in the left drawing is moving counterclockwise. So this guy is moving counterclockwise with a constant speed v around a circular section of the road. The drawing on the right shows the car and 4 possible directions for the centripetal acceleration that it experiences. So the centripetal acceleration is always directed to the center of the circular part, so it's going to be towards this direction, to the center. So these are not correct. So this is correct for the speed, but the acceleration is that way. Is that okay? The centripetal acceleration. Except if it's not moving with constant speed, and then we can have another tangential acceleration there, from where we can get a net acceleration between the tangential and the centripetal. But when we're moving at constant speed, then you only have centripetal acceleration towards the center of the circle. So the correct one is 4 right there. Okay. Next problem. Focus on concept question 03. Says two cars are driving at the same constant speed v around a racetrack. However, they are traveling through turns that have different radii, as shown in the drawing. Which statement is true about the magnitude of the centripetal acceleration of each car? So this one has a smaller radius, and this one has a larger radius. That's all we know. And centripetal acceleration is centripetal. This marker is bad. A centripetal is v squared over r. So centripetal acceleration is inversely proportional as r. So if r increases, this is small. If r is small, this is large. Say the magnitude of the centripetal acceleration of car A is at a greater than that of car A is greater than that of car at B. No. Since the radius of the circular track is greater at A. Oh no. So this is correct, but this circular track is not greater at A. Okay, the circular track has a radius greater at B, so that's why this is wrong. The magnitude of the centripetal acceleration of the car at A is less than that of the car at B. No. The magnitude of the centripetal acceleration of each car is the same. No. The magnitude of centripetal acceleration of the car at A is greater than that of B. Let's look at the reason. Since the radius of the circular track in A is smaller, so the smaller the radius, the higher the acceleration. So that is the correct answer for that one. Okay. Okay. Next. So it says a car is rounding an unbanked circular turn with a speed v, 35 meters per second. The radius is given. You are asked for centripetal acceleration. So v squared over r is 35 squared over 1500. So you just do that on your calculator. So let's bring that out. So do 35 squared over 1500. So give us our centripetal acceleration. See what that gives us. 35 squared. So this is 1225 over 1500. Okay. So 1225 divided by 1500. 0.82 meters per second squared. So that is what we have there. That's focus on concept question 04. Now let's look at question 05, focus on concept. And it says a small cylinder rests on a circular turntable that is rotating clockwise at a constant speed. Which set of vectors gives the direction of the velocity v and acceleration a of the cylinder and the net force that acts on it? Is that okay? So the net force that acts on it is going to be a downward force as it's going around. Is that okay? So this one, not this one, not that one. But let's look at the speed and acceleration. So as it's right here, this top, the acceleration will be going down. Is that okay? Is that okay? And then the speed will be going this way because it's going clockwise. So if it's rotating clockwise, at this point your speed is tangential, your acceleration is to the center, and the net force is going down at that point also. So the correct answer would be 4 for that case. A small cylinder rests on a circular turntable that is rotating clockwise at a constant speed. The cylinder is at a distance of r centimeters from the center of the turntable. The coefficient of static friction is given. What is the maximum speed that the cylinder can have without slipping? So we're going to have the centripetal acceleration. So our centripetal force is mass times centripetal acceleration, is mv squared over r. So this is going to be equal to our frictional force now that is producing that. Okay? So the frictional force is mu times normal force. So mu times normal force is mv squared over r. And since this mass is resting on the cylinder, so the normal force is just the weight. When you're on a horizontal flat surface, your weight is your normal force, right? So this is mu mg equals mv squared over r. So the m's cancel. So they're asking us to find the maximum speed, V max, which is this. So V will be mu gr square root. So mu gr square root will be 0.45 times 0.12, 12 centimeters. We convert that to meters. 0.45 is your mu times 0.12 your r times g, 9.8, and square root of that. So let's do that and see what it gives us. So 0.45 times 0.12 times 9.8, square root of that, 0.73 meters per second, exactly. 0.73 meters per second, exactly what we get there. So that becomes our V max for this case, okay? So let's look at the next problem. It says a car travels at a constant speed around a circular track whose radius is given to be that. The car goes once around the track in 2:35 seconds. So that's like giving you the time it takes for one cycle. That's like a period, right? So what is the magnitude of the centripetal acceleration of the car? So we're going to write another formula for centripetal acceleration. Centripetal acceleration is v squared over r. So v is omega r square over r. So this is omega square r square over r. So centripetal acceleration has another formula, omega squared r. But omega is 2 pi frequency. And frequency is 1 over period. So this 2 pi over period is the time it takes to go around once. So I put that in here. Centripetal acceleration becomes omega squared 2 pi over period squared r. Yes. So I'm giving the time, I'm giving the period, I'm looking for the magnitude of the centripetal acceleration, and I'm giving the radius. So this is solved, okay? So this becomes 4 pi squared over t squared r. 4 times 3.142 squared times r, the radius, 3.23 kilometers, 3230 meters, divided by 235 squared. Okay, so let's do that and see if we get that answer they have there. So I converted the kilometers to meters, 3.232 times 1000, 3230 times 3.142 times 3.142, just squaring that, times 4, divided by 235 squared. 2.31. Exactly what we have there. 2.31 meters per second square. Okay? That solves that. 2.31 meters per second square. Okay? Good. Now let's go to the next problem. It says, how long does it take a plane traveling at a constant speed of that to fly once around the circle whose radius is given to be that? Is that okay? So we have the radius, we have the speed. We are looking for the time it takes to go around 1. So we're going to use this again. We're going to use this again, okay? Okay. So let me clean here. So I know that v squared over r is omega squared r. So those two are equal, right? They are equal. So if they are equal, I'm giving the speed v. Is that okay? I'm giving the radius r. So I know omega is 2 pi over period squared r. So I can get my period from here. So let me do that. V squared over r squared equals 2 pi over t squared. So the square goes away. V over r is 2 pi over t. So this is just v is omega r. Is that okay? This is just v is omega r, where omega is 2 pi over t. So it's the same. I just derived it from a different way. So now find t. So t is 2 pi r over v. That's the time it takes for one to go once. Is that okay? To go around the circle once. So it's going to be 2 pi times 4410 divided by v, 176 meters per second. Is that okay? So I do that really quick. 2 times 3.142 times 4410 divided by 176. 157.5. 157.4 something. So just 157 actually. 157.4 57 if you like seconds. Okay? Just says 154. Okay. Now we'll go to a problem. That was problem 05. Problem 14, chapter 5. At an amusement park, there is a ride in which cylindrically shaped chambers spin around the central axis. People sit in seats facing the axis, their backs against the outer wall. At one instant, the outer wall moves at a speed of 3.83 meters per second, and 64.3 kilogram person feels a 403 Newton force pressing against his back. So the force you feel pressing against your back on this wall is what furnishes your centripetal force. So that force pressing your back, which is 403 newtons, will be mv squared over r. It will be centripetal force. Is that okay? Is that okay? And that's what solves. So what is the radius of the chamber? So we just do this. So we just solve that. 403. So do that up here. So I have 403 equals mv squared over r. So the mass is given 64.3 kilograms. Times the speed is given 3.83 meters per second. Over r. We are looking for r, and the speed is squared, okay? So r becomes 64.3 times 3.83 squared mv squared divided by 403. Divided by 403. So let's see what that gives us. So 3.83 squared times 64.3 divided by 403. 2.34. 2.34 meters. Exactly what we have there, okay? Exactly what we have there. So that's the answer for that. Next problem. So next problem says, let's take a look at that really quick. Computer-controlled display screens provide drivers in the Indianapolis 500 with a variety of information about how their cars are performing. For instance, as a car is going through a turn, a speed of 94.1 meters per second, the centripetal acceleration is given 3.81 times g. Determine the radius. So it's simple. You're given the acceleration 3.81 g. So that's 3.81 times 9.8. That's your acceleration. And you are given the velocity they are going, the v, or the speed, is 94.1 meters per second. So you're looking for r. So a is v squared over r. So r becomes v squared over a. So that is 94.1 squared over this a, 3.81 times 9.8. And that solves the problem, okay? So let's do that real quick with our calculator. 94.1 squared divided by 3.81 times 9.8. 237.2. Yeah, 237. 237.2. That's my radius, okay? Meters, okay? That's what it is. So that's problem 5, chapter 5, problem 9. Now we'll go to chapter 5, problem 22. It says a 940 kilogram race car can drive around an unbanked turn at a maximum speed of that for 3 meters per second without slipping. So let's wipe this off. Get something to clean this better. 1 second. Okay, so a 940 kilogram race car can drive around. Wipe this off. Alright. A 940 kilogram race car can drive around an unbanked turn at a maximum speed of 43 meters per second without slipping. The turn has a radius of that. Air flowing over the car's wing exerts a downward pointing force called the downward force of 9600 Newton on the car. What is the coefficient of static friction between the track and the car's tires? Okay. So we're going to get frictional force. I want to be the maximum speed if no downward, if there was no, if no downward force acted on the car. Okay. Okay. So let's see that. Is that okay? We're given the maximum speed. We have the mass of the car, so we can get the acceleration. Is that okay? So the centripetal acceleration is v squared over r. That is 940 squared. 43 squared. 940 is the mass. 43 squared over r, 200. So let's see what that gives us. 43 squared divided by 200. 9.245. 9.245 meters per second square. So what is the centripetal force? Is mass times centripetal acceleration. 940 times 9.245. So that times 940 gives me my centripetal force 8690.3 newtons. So this centripetal force, is that okay? Is that okay? Is going to be the frictional force. Is that okay? Without slipping. So that frictional force is the one producing that centripetal force. Okay? But we know that frictional force is mu times normal force. Is that okay? So normal force, the car is on the surface. So the normal force is just the weight plus whatever downward force is acting on it. So that would be the normal force going up. Okay? It's on the flat surface. So we have downward force 9600. The weight will be 940 times g, mg. So my normal force, Fn, will be weight plus downward force. So that is 9600 plus 940 times 9.8 mg. Okay, that's for the weight. So let's do that. 9600 plus 940 times 9.8 . 18812. So this is my normal force. So now I can get my mu. My mu is frictional force over normal force. That will be 8690.3 over 18812. So I have 8690.3 divided by the answer I just got, divided by 18812, 0.462. Exactly, 0.462. It has no units. So that is exactly what we get for the mu, okay? Get your centripetal force, mass times centripetal acceleration, that equate that to your frictional force. And then get your normal force, the downward force plus the weight, and then from there get mu using this equation, okay? Now, if there was no downward force, okay, if there was no downward force, and the second question, so what would be the maximum speed? So if there was no downward force, we'll walk backwards. The normal force is just going to be the weight, which is 940 times 9.8 alone. So if the normal force is just 940 times 9.8 alone, our frictional force is going to change. If our frictional force change, our acceleration will change and our speed will change. So we're going to walk backwards now, okay? So let me wipe this off so we walk backwards. So let's walk backwards. So our normal force is just weight, 940 times 9.8 mg. And that gives us, let's do that, 940 times 9.8, 9212 newtons. So our mu stays constant, it doesn't change. So mu is 0.462. So what is frictional force? Is mu normal force. So that's 0.462 times 9212. 0.462, 4255.944 newtons. So these are frictional force. So this frictional force is mass times centripetal acceleration. So centripetal acceleration is frictional force over mass. That's 4255.944 divided by 940. Okay. .5276 meters per second squared. So equate this to v squared over r. So your v becomes r times that 4.5276 square root. Okay. So that becomes, our radius is still the same. It's given 200 times 4.5276. And square root of that times 200, take square root of that, 30.1 meters per second. So without the downward force, is that okay? You have less maximum speed. But with the downward force, you have more maximum speed. All right. So we're going to go straight to the next problem. So suppose the surface of radius r of a cylindrical space station is rotating at that speed. To provide artificial gravity, what must be the value of r for the astronaut to weigh that? So the weight, since it's rotating, so the weight is now going to furnish the centripetal force. So that is simple. So what that means is, so what that is telling us is the weight, 1/3 times their earth weight times mg equals mv squared over r. Yep. So you're looking for r, you are given v. So m cancels m, 1/3 of 9.8 is v squared. The V given is 33.9 squared over R. So from here we'll get R. R is 33.9 squared times 3 divided by 9.8. Let's see what that gives us. Okay. 33.9 squared is that times 3 divided by 9.8. 351.8. Exactly. 351.8 meters. So we're going to that was problem 34. Now we'll go to problem 36. It says a satellite circles the Earth in an orbit whose radius is 5.19 times the Earth's radius. The Earth's mass is 5.98 and the radius is that. What is the period? So this is the period. So this has to do with Kepler's third law, which we can derive right here to get the period. It's a centripetal force problem. So as you are going around, the satellite is going around, the gravitational force, G, mass of Earth, mass of satellite, divided by radius of Earth, where is it? So the radius is given, is that okay? That it's circling around. So I'll just put it as R, is that okay? The orbit, is that okay? Square. So this is equals m of satellite v squared over r. You see that? But this is the same as m of satellite omega squared r. And I know what omega is. M of satellite, omega is 2 pi over t squared r. So mass of satellite cancels mass of satellite. Okay. Then I'm looking for t. So how do I get t from here? R goes down. G mass of Earth over r cubed is 2 pi over t squared. So 2 pi over t is square root of G mass of Earth over r cubed. So what is t? T becomes 2 pi r to the 3 over 2, that's square root of r cubed, divided by square root of G mass of Earth. And that solves the problem. So we just put all the values there. Use your R to be 5.19 times radius of Earth, 6.38 times 10 to the 6. And use G, so put R here to be 5.19 times 6.38 times 10 to the 6. And then use G to be 6.67 times 10 to the power negative 11. And use mass of Earth as is given there, 5.98 times 10 to the power 24 kilograms. And put that in there. Put it in here with everything. You're going to get the period to be exactly 59945.8 seconds, as it's given right there. 59945.8 seconds. Okay. That solves that. Okay. So this is the formula for the period, but you just have to derive it using gravitational force equals centripetal force. Then you get everything. Let's go to focus on concept question 03. We're talking about work, energy, and power right now. Okay. So it says a force F acts on an object undergoing a displacement S. The force being oriented at an angle theta with respect to the displacement. Which one of the following correctly describes all of the circumstances under which the work done by the force is zero? So we have a force acting on an object at an angle theta. How can this force do no work? So let's look. The force is zero, that's a possibility. Or the displacement is zero, that's a possibility. Or the angle is 180 degrees. No. If the angle is 180 degrees, you're still going to get cosine theta to be minus 1, so there is still work. The displacement is zero, or the angle is 90 degrees. The displacement is zero is correct. The angle is 90 degrees is correct, but there is still another one, so that's not complete. The force is zero, so it describes all of the circumstances. That describes only two, but not completed. So that's correct, but it's not complete. That's why it's not describing all of the circumstances. The force is zero, or the angle is 90. It's not describing all the circumstances. The force is zero, or the displacement is zero. It's not describing all the circumstances. The force is zero, the displacement is zero, or the angle is 90, because cosine 90 is also zero. So that is the correct one, E, right there. Okay. Focus on concept question 5. A 3-kilogram model airplane has a velocity of that, and a velocity of that due north. What is the plane's kinetic energy? Is that okay? So you have a speed, a velocity due east, and another velocity due north. So we're looking for the plane's kinetic energy. Okay? So we have the components of the velocity. Kinetic energy is a scalar quantity, so let's just get one velocity, which is 5 square plus 8 square square root, since it's east and north. Is that okay? So east and north this way. Is that okay? East and north this way. So my resultant velocity will be like that. And the resultant velocity will just be the square root of the sum of the squares of the individual velocities, right? So my resultant velocity is just square root of 8 square plus 5 square, square root of 64 plus 25. Is that okay? Square root of 89. Is that okay? Good. So let's look at square root of 89. .434. So now, what is the kinetic energy? Kinetic energy is half mv squared. Half times 3 times 9.434 squared. So v squared will just give us 89. So half of 3 is 1.5 times 89. So let's see, 1.5 times 89. $133.5, 134 joules. So the first is to get your net velocity, and then just do half mv square. And half mv square, that solves the problem. Okay. That's focus on concept question 05, focus on concept question 09. Force F1 acts on a particle and does work W1. Force F2 acts simultaneously on the same particle and does work W2. The speed of the particle does not change, so it means the work doesn't affect. From both of them, they don't do anything. So which of the following must be true? W1 is positive, W2 is 0, no. It means W1 will do more work. W1 is positive, W2 is positive, no. W1 is 0, no. W1 is minus W2, yes. So they cancel out. That's why the speed stays the same. Because if not, if there is net work, you're going to have kinetic energy and the speed is going to change. Is that okay? Is that okay? So the correct answer is D. Chapter 06, problem 01. During the tug of war, Team A pulls on Team B by applying the force of that. And then how much work does Team A do if they pull Team B with that distance? So it's just the force times the distance. 1770 times 3.07. And then just give you that joules. Is that okay? Force times distance in the direction, or force times the displacement in the direction of the force. So let's go to the next one. So it says a person pulls a toboggan, I don't know what that is, for a distance of that along the snow with a rope directed at that above the snow. The tension in the rope is that. How much work is done on the toboggan by the tension force? So now we have to get the component of the force parallel to the distance the force pulled the toboggan. Okay? Let's take a quick look at that. So you are pulling something at some angle. So the angle here is given to be 31.6 degrees, and the tension on the rope is 85.7 newtons. And you move a distance of 34.7 meters. Is that okay? So the component of this guy here is cosine 85.7 cosine 31.6 degrees multiplied by the distance 34.7. This is equals to your work done. Is that okay? FD cosine theta, if the orientation is like this. If theta is this way, then this formula will not work to be sine theta. Cosine theta if the theta is between the force and the horizontal. Okay, be careful. So just the force times distance cosine the angle between the force and the positive x-axis. That gives you your work done. Is that okay? So let's do that. See if it gives us the answer for the A part. So 85.7 times 34.7 times cosine of 31.6 degrees. 2532.86. 2532.9. Correct for the A part. 2532.9 joules. The B part said, how much work is done if the same tension is directed parallel to the snow? So no more angle. Parallel to the snow means no cosine. It's just 85.7 times 34.7. Okay? So the forces are the same, so I don't need to put any angle. So 85.7 times 34.7. 2973.8. Exactly. So it's just pretty straightforward. Pretty straightforward. Okay. And then we have the last problem for the homework. A 52 kilogram box is being pushed a distance of that across the floor by a force P. So I'm going to illustrate this in a diagram so you guys understand what's going on. So 52 kilogram box is pulled by a force P whose magnitude is 180 newtons. The force P prior to the displacement of the box, coefficient of friction is given to be 0.25. So mu is 0.25. So we know the weight of this guy. mg, which is 52 times 9.8, so we can get the weight already. So let me get that because it's going to be useful. So 52 times 9.8, 509.6 newtons. That's the weight. So my normal force will also be 509.6 newtons, since there is no force at an angle. So determine the work done by each of the four forces: the weight, the P, the friction, and the normal force. Okay. So this guy is pulling this guy this way. Is that okay? 7 meters across. So it's going 7 meters across. So this is my distance. Okay. Well, I don't know what my friction is. So friction is mu normal force 0.25 times 509.6. That gives me my friction. So I have all my forces. Okay, 509.6 times 0.25. So my friction is 127.4. 127.4 newtons. So what is the work done by P? Work done by P is just 180 newtons times the distance, 7. Work done by friction is 127.4 times 7, but there's an angle between them. Friction is going cosine 180 degrees, so -1 actually. You're just going to know it's negative because the force is opposite the direction of the displacement. So it's going to be a negative work done. So you multiply the force by the distance, but you put a -1 at the end, or you just take cosine the angle 180 to still bring the -1 there. So you're going to get a negative answer here. So let's just get the answers right. So for the first one, 127.4 times 7, 891.8, negative 891.8 joules for the friction. 180 times 7, 1260 joules for work done by P. What is the work done by the weight, mg? So you are going this way, your weight is going perpendicular. So perpendicular force doesn't do a work to a displacement in the other direction because cosine 90 is 0. So work done by mg is 0. And also work done by normal force is 0 because it's also perpendicular to the displacement. Is that okay? And that solves the last problem for this. I'll see you guys next week for homework number 6. Thank you.